All right, everyone. Now we're on our second problem, bend, don't break. So you have a ceramic beam, length, width, thickness. We're loaded here. If we have our coordinate system, x and y, we're going to say we need to kind of set up e dot I dot y quadruple prime x minus 30 delta x minus L divided by 4 minus 4.5 times 10 to the 3 x minus 5L divided by 6. And we have our y of 0 equals 0. If this is x equals 0, this is x equals L. Our y prime of 0 equals 0 for our boundary conditions. This problem, because we know that there's going to be a reaction force here, a reaction force here, a reaction moment as well. So we are actually statically indeterminate in this problem, so we actually have to use our boundary conditions. So we also know that y of L equals 0 and our y double prime of L equals 0, y dot I, or e dot I. So now we can move on and start to set up our solutions. So what we're going to do is I'm going to pull up. We have a ceramic beam, so 300 times 10 to the 9, length of 61 centimeters. Oops, where's my 61 centimeters? A width, which is our B, of 25 millimeters, and a thickness of 0.17 centimeters. All right. So we've got everything defined in here. Let's go ahead and define our Dirac delta. So minus 30 times, not times 10 to the 3, Dirac delta, x minus L over 4. And then we'll do minus 4.5 times 10 to the 3 times Dirac delta of x minus 5L divided by 6. We can shift into that. We have our boundary conditions, y of 0 equals 0, y prime of 0 equals 0, y double prime, and I'm just going to, to be clear, y dot I times this double equals 0 here. That looks good. Let's go down. We're going to solve. I'm going to copy and paste this into here. And then let's go here. Let's look at our, what's the maximum displacement? And we should be pointing down, shift to the right, makes sense. I'm going to find minimum. I'm going to say look around probably 0.4 just to give it a little hint. Maximum displacement should be around probably minus 1.9 meters. Yep, 1.93 meters. What about the maximum stress? Let's look here. Let's go ahead. So let's go look at plot the moment. So our moment is maximized here. So let's find the maximum of the moment. Let's look at it around 0.5 here. And we should know that we are definitely in positive curvature at that location because our beam is kind of doing our smiley face at that particular location. I want to... Might have to... I don't want to abort this. Let's go ahead and let's abort the... Okay, I need to rerun my script. But I'm going to rerun it just from this solution here. And then I'm going to say, I don't really need, I do need this because I do want to solve, and I do want my shear as well. So I'm going to go ahead and say, that's probably a problem here. Let's define this. So let's define everything in here. It doesn't like that the graphics are not defined. Let's see if this works. Yep, 344, so I can plug that in. Again, we are definitely in, if we're looking at the top of the beam, we should be top of the beam or in positive moment, but we should be in compression, so we should have a negative stress. There we go. Fantastic. Where's the shear force maximized? Let's plot the shear. And we can see the shear will be maximized right here. So we can just say, for example, shear slash dot x goes to L. There you go. That's it. Anywhere here in terms of location, anywhere there, and we've got it. Fantastic. And actually, you'll probably get a question where instead of where this is maximized, I'm going to say justify that maximum stress value. All right, let's go ahead. Let's see here. Some dynamic classical testing curves, material A versus frequency, tested B and C. B is a liquid. C behaves like a viscous material that is more solid than material A. All right. So, draw the, let's see here. Let's see. So it's giving us, and let's verify it ourselves, at high frequencies it should be looking like a solid, and that is our G prime and our G double prime. There. So, draw the B and C storage and loss modulus. So what I'm going to do is, for me, I'm going to do B as in this, and then this is going to be my G double prime. This is going to be my G prime. For here, I'm going to say this is, and then I'm going to do the same kind of notation there. So B is a liquid. So if I'm a liquid, I'm going to say my G double prime is always going to be higher than my G prime for everything. Fantastic. If I am C, which is more solid than material A, so everything to the right here is looking more solid. So I'm going to have to actually do my dash is going to have to be like here, and then my solid is going to have to be like this. So I'm more solid than there. Rank each material's relaxation time and glass transition temperature. So we can actually do this right now. So we know that for a liquid, so for B, my relaxation time is basically 0. And that kind of makes sense on the frequency curve. And my TG is effectively 0 because we're already moving cooperatively. So that's instantaneous response. Now, in terms of the other ones, let's look at it from this perspective. This would be my relaxation frequency. This would be my relaxation frequency for my material, C or whatever it is, or yeah, material C. Yes. So if I look at this, my omega for B is greater than my omega for C. And I know that omega, like star, because this is a relaxation frequency, is inversely proportional to my relaxation time, tau. So if I have a high omega, that means my tau is very small. So that means my tau for C will be greater than my tau for beta. Or for B, excuse me. That makes sense. So the tau, because omega C is already larger here, to get that has to be, actually, excuse me. I've missed, see, this is the confusing part. So omega is, oh yeah, yes. So B, so materials, then omega C. So if omega C is very, very small, the tau, yeah, the tau of C is going to be greater than the tau of B. Yes, that makes sense. More solid, right? Fantastic. Because this is larger. Sorry, I'm confusing. This is always, see, this is a good example of kind of confusing myself. So if our omega here is large, or actually B omega is large, that means that has to be small. Exactly. We're good. And our tau of C, or TG of C must be greater than TG of B. And that makes sense. More solid, higher TG, longer relaxation time. We got it. Hard to, it can definitely confuse yourself, but everything matches. Fantastic. So remember, make sure, expect a problem where I ask you probably and said, justify why that maximum stress value is positive or negative, with reference to curvature and all that stuff. See you next time. Thanks.